Welcome to the Picture Language Seminar. It's a great pleasure to have Kaifeng Bu back here from Ohio State University. He's going to tell us today about a universal framework for Gaussian testing. Kaifeng wrote many beautiful papers on quantum information and related topics, and we're looking forward very much to your talk today.
Okay. Thanks, Arthur, for the introduction. Always very glad to go back to Harvard and introduce our recent work on quantum convolution and the corresponding application in quantum information and quantum computation. So today, I will introduce a universal framework for Gaussian testing. So I will use the fermion system as an example. And I would like to, but this framework not only works for fermion, but also works for boson and qubits and qubits. So here's the outline of my today's talk. So first, I will give a brief introduction of the background, like what is fermion system and what is fermion operator and what is the corresponding Gaussian states and the unitary in fermion systems. And then I will introduce how to use quantum convolution to design a protocol to test whether the given state is Gaussian and how to quantify the non-Gaussianity in the states. And later, I will make a summary and propose some possible future directions. And today's talk is based on the following three works. The first one is the collaboration with Nicholas, who is an undergraduate at Harvard. And then the remaining two is the collaboration with Wei-Cheng Gu, who is now a postdoc in my group, and also Arthur here, who was my postdoc advisor. Okay, so the reason we are care about the Gaussian testing is because we are interested in the boundary between classical and the quantum computation. So quantum computing quantum computation is now becoming a very, very popular topic in recent years. And people usually believe that quantum computer can be much faster than classical computer. Like Shor's algorithm provide some evidence for this argument. But in fact, there are several families of quantum circuits which look like quantum, which could have very large amount of entanglement. But this kind of quantum circuits can be simulated efficiently on a classical computer. So this families require us to rethink about where's the boundary between classical and the quantum computations, because it seems that not all the quantum circuits can have advantage. So we need to find out what kind of quantum circuits have advantage, what kind of quantum feature will support this kind of advantage. Okay, so, and we will give some possible answer. It's like the non-Gaussianity will support this kind of quantum advantage. And here is a family of classical simulable quantum circuits. For example, the stabilized circuits on qubit or qubit system, and the fermionic Gaussian circuits on Fermi system, which is also known as match gate circuits. And also the bosonic Gaussian circuits on boson system or the continuous variable quantum system. And today we'll focus on the fermionic Gaussian circuits, which is also known as match gate circuits. And this concept or this family was first proposed or introduced by Leslie Variant at Harvard back to 2002. And later, people like De Vincenzo and Giosa, they found that this kind of match gate circuits can be reinterpreted as like a free fermion or fermionic Gaussian circuits in quantum systems. Okay, so today I will show how could we use convolution to test whether a given state of a unitary is a Gaussian or not. So before introducing our results, let me first make a brief introduction of the background for Fermi systems. Okay, so let us consider a quantum system with n fermion modes. Which will have given permission minor Fermi operators. Gamma j, where j from 1 to 2. And the Fermi operators will satisfy the following anti-commutation relation. And the corresponding algebra generated by these two banana Fermi operators are called Clifford algebra. And the corresponding operator, like for any subset A from 2n, we can consider the corresponding fermion, the Fermi operator, which is the product of the Fermi operator supported on the set A. So which means it's a product of I in A. Of course, this is ordered like we record the product from the smallest to the largest. Okay, and one important property of this this set of gamma A is that it will form an orthogonal basis with respect to the inner product defined by normalized trace, which means any. So it is an orthogonal basis. So which means any state can be written as the linear combination of this gamma A, and the CA is the inner product between the given state and to the set of the gamma A. Okay. So and the trace is defined as the normalized. The inner product is defined as the normalized trace.
How to take a trace in this fermion system?
Oh yeah, because here we consider true and so we can say n fermion modes. So basically, you are still consider the trace on the big Clifford algebra.
Yeah.
So you can still do it like what you have done in the n-qubit system. So the only problem is like when you do the partial trace, you have this kind of problem. So if you do this big trace, that doesn't matter. Okay, so for the fermion system, we usually have some restriction on the parity. So for the if the set A is 2n, then it's gamma 1 to gamma 2. So the product of all the fermion operators and will define the parity of fermion number operator, and we will require the parity of the state will be conserved. So under this case, you will see like we will be introducing the concept is called the even state. So log is the even state. If in the decomposition of the Fermi operators in this form, CA is equal to 0 for any subset A. Whose size is tall. So for this kind of even state, you will find that it is always commuting with this the parity of the the product of all the gamma I from 1 to n. Okay, so this is the even state. And now with the even state, we can define the basic concept called a Gaussian state. So an even state low is a Gaussian if it is it can be written as the thermal state or some quadratic Hamiltonian. And the H is a quadratic Hamiltonian, means it can be written as the form which only have quadratic terms of the Fermi operators. And here to make the H is to be a Hermitian operator, we require the matrix of Hij is anti-symmetric. Which means the transpose is equal to minus H. Okay, so this is the basic definition of Gaussian state, and you can see the Gaussian state is the thermal state of some non-interacting Hamiltonian. And similarly, let me first here give some example of Gaussian state for n modes. So because the H is a anti-symmetric matrix, so it can always be decomposed as the following form. So it can be decomposed as some rotation matrix and some direct sum of diagonal matrix. Yeah. It's so good. So this is a basic property of the anti-symmetric matrix. You can have this kind of diagonal. And then the Gaussian state can be written as exponential to the power of beta H. Now the H is like this form, so you can define the gamma tilde to be the rotation matrix on the gamma. So it will. So in this new basis, gamma tilde, the Gaussian state can be written as this simpler form. And because each quadratic term are commuting with each other, so you can rewrite this the product state in the new form. Okay. So this is the basic form of the Gaussian state. Now we can consider the Gaussian unity. Okay, so Gaussian unitary is Gaussian if it can be generated by some quadratic Hamiltonian. This is the basic definition of Gaussian, and the unitary is a Gaussian if it can be written as some exponential to the power of some quadratic Hamiltonian in the fermion basis. Okay, and then one important property of the Gaussian is the Gaussian unitary will preserve the degree of the Fermi operators. So what that means, it means when a Gaussian unitary, when it's acting on the minor Fermi operator gamma I, it can always be written as some rotation matrix R acting on the minor fermion generators for any. So this is the basic property of Gaussian unitary, and then we will use this basic property to show why the fermionic Gaussian circuits or match gate circuits can be simulated efficiently on a classical computer. Now we go to a very important result. The classical simulation of fermionic Gaussian circuit. Okay, let us consider the circuit with n input states, like one-dimensional n-qubit system. And then the circuit is a fermionic Gaussian unitary, UG. And after that, we'll take a measurement, for example, in the first qubit, in the computation basis. So we'll get the output probability P0, P1. And we will find that this P0 and P1 can be computed efficiently on a classical computer. So here efficiently means it can be computed in polynomial time on a classical computer. And the reason it can for this efficiently simulation on a classical computer is so the output probability, for example, 0 is somehow equivalent to UG dagger and the 1 plus 0.2 0.1. Okay, so because the identity is trivial, so basically you to show the output probability can be similarly efficient on classical computer is equivalent to show the expectation value on poly Z can be computed on polynomial time. So we only need to show the expectation value can be computed efficiently. And the reason is we can, because this is a one-dimensional n-qubit system, so we can use the Jordan-Wigner transform to map Z1 to gamma 1, gamma 2. And then the conjugate action of the Gaussian unitary on the minor operators gamma 1 times gamma 2, based on this key property, which will map the generators to the linear combination of the generators. So it will become the summation of Mj gamma G, the summation R1K. So there are like a 2 to the 2n terms. There are also 2n terms. So their multiplications have 4n squared terms. So there are 4n squared terms gamma J times gamma K, and so we only need to show each quadratic term on n-times product of zero state can be computed efficiently. And this can be done for one-dimensional qubit system because you can use Jordan-Weaver transform. So gamma j times each gamma z is a times product of single qubit Pauli operators. So gamma j times gamma k is also a times product of Pauli operators. So this can be each term can be computed in order of n pi. So there are 2n square of this kind of term. So total number is like still polynomial. So this is the basic reason, the Gaussian unitary can be fermionic Gaussian circuits can be computed efficiently on classical computer. And then natural question is, given a quantum state or quantum gate, how could we decide that this is a fermionic Gaussian state or unitary or not?
Here you only measure the first one. Do you consider measuring all of them?
Yeah, you can also do consider measure all of them. So this is just one example. There are some variants of this protocol, but you can still show it to be efficiently similar. So I just give one example to show why the Gaussian unitary can be similarly efficiently. So basically, the Gaussian unitary will preserve the degree of the minor Fermi operators. Okay. So the question is, given a state, how could we test the given states of gates is fermionic Gaussian? Once we could do that, we may also could quantify the non-Gaussian in the states. So this is the basic two questions we will try to answer in today's talk. Okay, and so let's go. So let us move to the second part. How could we do the Gaussian test and the non-Gaussian measure? Okay, so recall that in the classical probability theory, the Gaussian distribution usually have very good behavior under the convolution. So once we have two Gaussian random variables, we do the convolution of these two Gaussian random variables. Then the output random variable is still a Gaussian. So we will. So this provides us some intuition. Maybe we should develop some framework of quantum convolution to solve the problem or to study the problem of Gaussianity. So here, we will consider the fermionic convolution. Okay, so this concept is not a new concept. The fermionic convolution was first invited or introduced by Hartley back to 1973. At that time, he introduced the fermionic convolution for even states, and then they show and then he showed some fermionic central limit theorem, which means if you keep doing the convolution again and again, finally the output state will converge to a Gaussian state. And here we are not concerned about this mathematical result. We are trying to use this fermionic convolution and try to use it to test whether the input state is the Gaussian. So this is our major contribution. So now let me first get the definition of fermionic convolution unitary. So first let us introduce the fermionic beam splitter. So everyone may be familiar with the bosonic beam splitter in the continuous variable system, like in the continuous variable quantum information theory. But here I will introduce the fermionic beam splitter, which will be useful to introduce the fermionic convolution. Okay. So the fermionic beam splitter on two fermionic modes is defined as theta 1 summation of gamma d. So this is the definition of fermionic beam splitter, and based on this definition, you can see it will act on 4n minor operators, which means it will act on 2n minor modes. Okay, so
Sorry, is that a 2n plus j then? Yeah.
oh yeah, it's a 2n plus j. Yeah.
Is that modulo 2n? What is it? I thought there were only 2n.
Oh yes, like first let me draw the circuit.
Oh, wait, because you didn't define the minor modes yet.
Yeah. I don't define my nodes. I just directly use the minor operators.
Okay, good. That's
Yeah.
fine. Okay, I'm fine. I'm fine.
Yeah.
Okay.
Okay. Yeah. So basically, what we want to do is, so both rho and sigma are two n minor mode state, which means it can be described by the linear combination of minor fermion operators on of two n minor fermion operators, and then we require both rho and sigma to be even. So then there will be no problem of canceling together. Otherwise, if they don't have the same parity, it's very hard to define the tensor product of these two states. And then we apply this big unitary W sigma, which is the fermionic beam splitter. Okay. Then we take the partial trace on the second system. So this is the basic definition of the fermionic convolution. And why this can work very well? Because let us look at the action, the conjugate action of this fermionic beam splitter on the generators of the minor fermion operators. So it can be, it's just a location between gamma j and the gamma 2n plus j. So for any j from one to 2n. So the action of the fermionic beam splitter is just like the bosonic counterpart. It will just rotate the generators by some cosine sign, but by some zeta rotation. That's the reason why we call it fermionic beam splitter. It's almost the same formula. Okay. Okay. So the fermionic convolution is defined as the partial trace 2 so this is our definition fermionic convolution. Okay, let me emphasize again, this is not our original definition. This was first introduced by Hudson in 1933, and they also used it to show some fermionic central limit theorem. But our contribution here is the following key observation. So we will find that the Gaussian state, or the fermionic Gaussian state, is the fixed point of the fermionic. Okay, so this is a roughly it's the roughly speaking. So the fermionic Gaussian state is the fixed point of the fermionic convolution, and the more formally or more mathematic formally, we can show for any pure state, which is even, convolution with itself is still pure if and only if the sign itself is a Gaussian. So this is what we mean the fermionic Gaussian is the fixed point. So somehow the purity is preserved after the convolution if and only if it is Gaussian.
I'm sorry, are Gaussian states, can't they be mixed as well as pure?
Sorry,
Can't they be mixed as well as pure?
yeah, a Gaussian state can be mixed and it could also be pure state. So the based on the definition, the Gaussian state is the thermal state. If you look at this formula, so the Gaussian state is the thermal state of some quadratic Hamiltonian.
Right.
When it's final temperature, it will be mixed. It will like when it's go to like a term limited, it will be a pure state.
Yeah.
Okay. So here we are focused on the problem like given a pure state. Of course, this argument also works for mixed states. But now let us focus on the pure state, which make the situation simpler. But the idea are similar.
Right, I'm sorry, I just like. When you said psi.
Yeah.
Psi convolution with itself is pure.
Oh, yeah, let me-
Psi is Gaussian.
Yeah, so we give a
you
pure
were
state.
assuming psi was pure.
Yeah, we give a pure state.
Okay, that's what I was thinking. Sorry.
Yeah, sorry. We assume like we have an input state which is pure state, and we want to test whether the pure state is a Gaussian.
Good.
Okay, now what do we find that is it is Gaussian if and only if after the convolution with itself is pure. Okay, then it means if we want to check the psi is a Gaussian, which looks not so obvious, then based on this property, it's equivalent to checking the convolution is pure state. Okay, check a state is a pure state will be much simpler than checking a state is a Gaussian, because there's a very standard subroutine in quantum computation called swap test to test the inner product of the two input states.
So this percent can be mixed or can be pure.
Well, here we're given a pure, but for mixed, because we needed to consider the original the purity of the input state.
Yeah.
We can still use we can still use this argument if you know the purity of the input state. Okay, so it seems that I have to use this. Okay, now let me introduce the swap test, which is a very, very fundamental subroutine in quantum computation. So for any two states, then we can apply the control swap gate and also some two automatic gates, and measure the first the control qubit, then the output probability to get 0 is equivalent to 1 trace of rho and C. Okay. So this is the swap test, which is a very standard subroutine for the swap test. And then how could we use this swap test to check this sub-convolution state is a pure state? So it's very simple. So we can just prepare 4 copies of the input state, and for each 2 copies, we can apply the convolution. And then we will get 2 copies of this self-convolution state. Okay, now what we need to do, we just put another swap test here. Then the swap test is just the inner product of the 2 integral state. Now the inner product, both rho and sigma, are the self-convolution. So the probability to get 0 is equal to 1 plus trace the self-convolution square. So let me use the inner product 2 states this way. So the output probability is equivalent to the inner product between the self-convolution and itself. And it's equal to 1 if and only if. Okay, so which means if the probability is less than 1, then it's a non-Gaussian. So you may have some, so we can based on this protocol to check whether the input is Gaussian or not. Okay, so here we based on the fermionic convolution, we constructed some a protocol to test whether the input pure state is the Gaussian or not. And here we only need to prepare 4 copies of the input state, which seems already very small number of copies, but in fact we can reduce the number of copies to 3. How could we do that? There's another property too. So here we found that the self-convolution is pure and only if it is Gaussian. And in fact, we can make more precisely. So the input state for any pure state psi, the input after the self-convolution, the output state is still precise but only flex Gaussian. Okay, so based on this property, we can prove then we do not need to prepare 2 copies of self-convolution. We just need 1 copy and then do the swap test with itself. Okay. Similarly, the output probability is equal to the now it's inner product between some convolution with the input state psi. And it's equal to 1 if and only it's Gaussian. Okay, so we don't need 4 copies, only need 3 copies to do the to test whether the input pure state is Gaussian or not.
But the can succeed.
Yeah.
If it can still succeed in the state is not Gaussian, right?
What
Because
do
you
you
just do
mean?
it once.
Yeah, sure. So because for the swap test, what we usually need to do is to need to sample it out. So what are you asking? Like, what's the behavior like when it is like the epsilon far away from the Gaussian state? So we can show like that if it's the probability. So if the given state is epsilon far away from Gaussian state, the output probability will have some lower bound value of 1 minus epsilon. So in some situation, like the Gaussian state, for example, as I said, this framework does not only work for fermionic Gaussian, and in the stabilizer case, we can show exactly when the state is epsilon far away from Gaussian, then the output probability, like to get 0, is 1 minus constant times epsilon. So somehow the probability will tell you how far away the given state is to the set of Gaussian state. Okay, so this is a very question, a good question. So here I consider perfect case like it's a Gaussian or not. But sometimes the input state may be epsilon far away from Gaussian. So this test will still tell us the information like how far away it is from away from the set of Gaussian states.
How do you measure the distance?
Oh, the distance is very simple. So you mean here. So it's just the like the trace distance. Okay, any other question or comment? Okay, if not, let me continue. Okay, here we use the swap test to test the whether the given input state is Gaussian or not. And basically, what we are doing is like using the purity of the subconvolution to show whether the input pure state is a Gaussian or not. So somehow the purity of this subconvolution state tell us the information about the Gaussianity or non-Gaussianity of the pure state. And there's a natural measure widely used in quantum information to quantify the purity of some state. It is the volume entropy. So let us move this idea for a little bit further. So we can use quantum entropy or volume entropy. So to quantify the purity. Of the subconvolution of psi. So which means we can define the entropy of the subconvolution state. And here we call it non-Gaussian entropy. I will show the reason why we call it non-Gaussian entropy. Okay, the reason is following. So first, the entropy is always for any pure state, it's always less than equal to n and larger equal to 0. And equal to 0 if and only if psi is a Gaussian. Okay, so basically it tells us that the if it's non-zero, then the psi is a non-Gaussian state. And moreover, Ng is invariant on the Gaussian unit. So basically, once you have pure state psi, and then I have a Gaussian, any Gaussian unit Ug acting on psi conjugately, then the non-Gaussian entropy for this new pure state is the same as the original pure state. So it's invariant. So somehow this can be used. This property guarantee this entropy will or it's good for quantifying the non-Gaussian in the state. And moreover, we find that it's additive. So once you have test product structure, also additive. So these three properties can provide us some evidence. Ng can be used as a measure to qualify non-Gaussian. So we move the idea of the purity of the subconvolution a little bit further. Use the quantum entropy to qualify the purity and use it to qualify the non-Gaussian. And this idea is very familiar to us because we already met it in quantum information theory back to the entanglement theory. So let us consider what's the connection with the entanglement testing or separability test. Okay, So when we talk about the entanglement, like we have a bipartite state, A. So which is a pure state, pure bipartite state. And it is called it is separable if it can be written as phi A phi B. Otherwise, it's called an entanglement. So based on this transporter structure is a widely used measure called entanglement choke, which is basically used the purity. So we consider the reduced state of low A and consider the volume entropy of low A to quantify the entanglement choke. To qualify the entanglement between A and B. So let us call it entanglement between. So the idea of entanglement testing or separability testing, or the qualifying of the entanglement for entanglement is just to use the purity of the reduced state after taking partial trace to qualify how entanglement the original bipartite state is. And this is quite similar to our ideas like how to use the purity of the subconvolution to quantify the amount of non-Gaussian. And in fact, if we consider the definition of our convolution, the entanglement. So basically what we did here is we have two mode fermion systems, and we use the fermionic beam splitter to correlate them together or to entangle them together. So there we'll have some entanglement. And then we call the output state is like psi AB. And then what we do is take the partial trace on the second system, and this is a reduced state on the first system. And this the reduced state what we call the subconvolution. And it is in fact the reduced state of low A, which means it is the entanglement A and B for this side. So somehow what we did, we somehow using the fermionic beam splitter to correlate the two input states together, as they use the entanglement of the output state to detect or to test and then qualify the non-Gaussian. And the reason it happens is because the Gaussian state is a fixed point of the convolution unit. Okay, so this is the basic connection between our framework and the separability testing, and you can from the quantum physics point of view, you can reintegrate this as using the quantum entanglement to measure non-Gaussianity. Here, the non-Gaussianity could be either in the fermionic system or also in the continuous variable system, also in the qubit coded non-stable line. So, yeah, okay. So this is the basic material I would like to introduce into this talk. And before the end of the talk, let me make a short summary. So basically, in this framework, we introduce a quantum convolution, not only in fermionic system, but let me emphasize, we also introduce in the qubit coded system for stabilized state, and also the well-known beam splitter as like studied in the continuous variable system like Seth's work. We can use this kind of convolution of beam splitter operator in different quantum system, but we can use it to show they can be used to test the Gaussianity and to quantify non-Gaussianity. Okay, so I think that's the end of my. Thank you for your attention.
Thank you very much for an interesting talk. Are there any questions here?
I have this is a related question. So when you say this is a thermal state, do you have any interpretation of this temperature? Thank you.
Yeah. So basically, temperature is inherited in the like beta when I write the like e to the beta h.
Yes.
Yeah,
So,
and when the like it's well related to the like the mixedness and the purity. Like when it goes to the zero temperature, then it will become a pure Gaussian state for the quadratic Hamiltonian.
yes.
Yeah, so it's this kind of relation.
Is salt convolution entropy increasing?
Yeah, it's increasing. Oh, good question. So yeah, good question. Yeah. So if we keep doing the convolution again and again, so the reason why this we found this key property is because now this is not only for it's also go back to the mixed state question. For any state though, after self convolution, the entropy is always increasing. And the equality holds if and only though is the Gaussian.
Yeah, so do we need a better, I mean, you don't have to do it for your purposes, but maybe a better measure of the non-Gaussian entropy is S of rho convoluted with itself minus S of rho.
Yeah. This is also something we used in our paper. We call it the what is called we also call it the that's a very great question. Let me let me use this part. Yeah, we also use this one. So the entropy difference to qualify the non-Gaussianity, not only for the pure state, but also for the mixed state case. And we call it the W, quantum W constant. So one of our paper is to show this can also be used to as a measure of non-Gaussianity, and it's not only somehow evaluate on the Gaussian unitary. If we consider quantum channel, which are like the Gaussian, any common channel can be constructed by tensor some state and some joint action, conjugate action of big unitary and take partial traits. And if we restrict the state in the tensor product to be like Gaussian state, and the unitary to be Gaussian unitary, and let us call this kind of channel to be Gaussian channel. Then this is also monotone. This measure is also monotone on this kind of Gaussian channels. Okay, so this is another measure we mentioned in our paper. We call it the quantum W constant because it's just copied at the end of the convolution. And in fact, there's another one. So we can define another quantum divergence or quantum relative entropy, which is a new, like we can use the Brownian entropy, like a Poynting state rho and sigma. We can consider the entropy of rho, the convolution of rho and sigma minus S sigma. So this is like the entropy difference between rho and sigma. And why is this interesting? First, is somehow like you can think about the convolution is like if we restrict the sigma to be like the Gaussian state or pure Gaussian state, so rho times sigma is somehow like blow up by some unit distance. Because entropy is increasing, you can think about it like a blow up. And how could like the blow up the entropy difference between low once you blow up a little bit. So it somehow will be related to the spectral gap on the graph theory. Okay, so because the graph theory, like you can think about like when you have a graph and you have a subgraph, and we consider the uniform distribution of the subgraph, like the points, the vertices in the subgraph, and then you jump it like to the boundary, like a unit distance. So you will have a new subgraph, which is and then we consider uniform like the two uniform distribution on the original subgraph and the unit distance. Then you will have a new distribution on a slightly big graph, and then we consider the area or the volume, which is somehow like some version of entropy. because the entropy is like the quantifying capacity or the volume. So we call it rather divergence quantum. Yes. This is the rather divergence, and then you can minimization over sigma to the Gaussian. Gaussian. So it's another measure of a non-Gaussian RC. So, and they can show this is equal to 0 if and only if rho is a Gaussian.
That's the minimum distance for these sigmas.
Yes.
Can you show, or even, I've asked it as a question.
Yeah.
If I take the Gaussian state that I get by convolving rho with itself, an infinite number of times, right? Is that the closest Gaussian state to rho?
Yeah,
Yes.
sure. Yeah. Good question.
Okay, good.
Yeah. You are
Then
right.
the
Okay,
guess
let me
whether-
draw the picture. Yes. So once you have a state low, so we can keep doing the convolution like that. Low convolution is low.
Yeah.
And the low to any n times. And what's the lowest one? Okay, so yeah, sigma g is the limit of the convolution. And goes to infinity, and it's the minimum. So you take the low, which is respect to. So here the entropy is the divergence is the usual common relativity we usually consider. And then we can take the minimum of all the Gaussian. Then it's the sigma g, which is the limit. When you repeat the convolution many infinite times.
So I have one final question. You had many beautiful results that you've described.
Yeah.
Do you have a picture of what's next?
Oh, sure. Yeah. So there are many. So the reason this is a very good question. So the reason we call the quantum doubling constant is we constantly find that this number is also studied in the additive compactonics by Terrestrial and Bungry, this kind of famous mathematician, and then they developed the very modern and Fourier analysis structure or framework called higher order Fourier analysis. So here we are trying to develop the quantum higher order Fourier analysis. So basically, original Fourier analysis is like the linear transform or phase linear operator, and then we will consider phase quadratic or cubic or higher momentum unitary. And it will be related to for example, for the cubic system, it will be related to Clifford hierarchy. And we are trying to build the quantum higher order Fourier analysis and to use it to solve the Clifford hierarchy testing, and also use it to approximate any unitary outside of the Clifford unitary by the unitary operators. So we can simulate them.
So thank you very much. And we have to have you back next term to hear about those new results.
Thank you.